Okay. Description of step response. Firstly, suppose that we have time response like this one. This is xt, this is t. Okay? So we apply the unit step, the constant 1. Okay? Just like this one. And so we create just kind of output in here. The red one is the R xt. The black one is the ut. Okay, this is the xt. So first of all, we need to draw these things. This is the XSS. Okay, this is the state response. And so we have 0.9 times XSS values in here at this point, and also 0.1 XSS at this time. Okay, and so in this graph we will call it this time period as the what? The T rise time. Okay, this is the T rise time. And also we have the MP value in here, and also we have this TP, time peak, in here. Okay, this is the desired SS response, because we need to what? If we apply the 1, we need to get the 1, but we don't have it right now. Okay, and so this is the peak time. And also we defined another parameters in here, which we call it the T settling time in here. Okay, because in this case we have the some band in here, band for the settling. These parameters have the what? Some important feature to analyze the R system dynamic. If we have this response and if we analyze these terms, and so we will obtain the exact coefficients of the second order system. Do you get it? Am I? Okay. And so also we need to say that we have this error value in here. This is called the steady state error. Okay, and we always say that this is the underdamped response. Why? We have the oscillation value in here, and so we have the imaginary part at our roots, and also we have the stable root or negative root, because it's going to the what? It's going to the some constant value XSS, right? 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 Okay. So in this case we can write that this system has the feature of the second order one. Okay, but why? If we have any FD x dot dot plus cx plus kx, just like this one. This is the forced plus free response. But what is the free response of this term? The solution of the free response is equals to what? B times E minus zeta w and t times sinus w dt plus phi value. Okay? This is the free response. But why we use the zeta times wn at the over term of the exponential? Huh? Why the zeta wn at the place of the exponential? Because we have a time response, and so it's time constant. Just remember the previous slide. This is the time constant, and so if this is the time constant, exponential term should always be equals to this one. Okay? And so, what's the meaning of the free? At the free case, ft is equal to the what? Huh? Huh? 0. Okay? But what happens if I apply the what? The unit step. The solution of this xt can be written as to the what? 1 divided by k times 1 divided by square root zeta square times e minus zeta wn t times sinus natural or damped frequency wn times 1 minus zeta square times t plus phi plus 1. Okay? This is our solution for the second order system with phi value, which is equal to what? The tangent minus 1 zeta square divided by zeta plus phi. This is not hard. Just solving this equation gives us this kind of system response. Okay? In terms of the what? In terms of s squared plus q zeta w and s plus wn squared. Okay? The solution of x in general form for the second order system looks like. Okay? That's it. Why? What's there? Just say. The solution of this system equals to this one. Okay? That's it. In the previous slides, we have this kind of feature, right? And so, if we solve this equation in general form, we will get this time response for a given unit step. Okay? But the important part is that if we measure the maximum overshoot, settling time, rise time, and XSS, we can drive zeta wn. Okay? If we analyze or use this value to drive into the what, the zeta and wn, and so we can model this system based on the unit step signals. And so we can find the zeta and wn value from a given data set. Okay? That's it. That is so simple. But how we can drive the maximum overshoot or the rise time or the settling time for a given this signal? Okay? If you apply a unit step to any system, DC motor or hydraulic system or the what, some other system dynamic form, and so we will have this kind of output. And so we will have the what, the specific zeta and wn value. But how we can calculate this zeta and wn from the maximum overshoot MP, settling time TS, TR, and XSS? Because if we have this graph and also we have the MP, TS, TR, and XSS, right? We can measure, we can see it. So, in order to derive these forms, first of all, the maximum overshoot can be calculated with the what? With this one. To find it, we should take the first derivative form of this xt. Why? Because the maximum point is in here. If we take the first derivative, and so we reach the zero value at the derivative, right? That's it. And so if we have the xt form, and so dxt dt must be equal to the 0. And also 1 divided by k, if we take derivative of this term with respect to the time, and then we will have wn divided by 1 minus zeta square times exponential minus zeta wn t times sinus wn 1 minus zeta square times t, right? This is our equation. And so, which value of the t makes it equal 0? This term is a constant. This term is a constant. This term cannot be equal to the 0. And so we have this value, right? And so, what is the value of the sinus is equals to the 0? Huh? This should be equal to the what? N times pi, right? If we have the pi, and so sinus always creates what? The 0. And so, if this is the case, we can write this. N times pi is equals to what? Wn times 1 minus zeta square times t. Okay? And so this t is equals to the what? N times pi wn times 1 minus zeta square, right? But if we looking for to the what? The first point, which is equal to 0, and so this n must be equal to the what? Yes. And so this is called the t peak, which is equal to the what? Pi divided by wn times 1 zeta square. See? If we know the wn and zeta, we can calculate easily the peak time of this system. Yes, the first. Okay? If this is the case, and so, if this is the TP, and then, if we put TP into XTP, this equation, and so, we will have this solution, X max, right? Because it's the maximum point. And so 1 divided by k times 1 plus 1 e over minus p. I'm putting just only the equation. Zeta divided by square root minus zeta square. Okay? So, what is the value of the MP? See that the MP is the maximum point minus XSS, right? It's the values of the what? This is the X max, this is the XSS, and so MP is equal to the what? X max minus XSS, which is equal to the what? XSS 1 divided by K times E minus pi zeta divided by minus 1 minus zeta square, right? Because the X max is equal to this one, XSS is equal to this one, and so this is equal to the what? This term. Okay? And so, if this is the case, how we can convert this value into the percentage value? If we have this MP, and so we can continue this one. if we have MP percentage is equals to what? X max minus X SS. This is the MP. But if we divide the X SS, this is going to be the percentage representation of these terms, right? Times 100. And so, if this is the case, 100 times E minus pi zeta square root minus zeta square, which is equals to what? The maximum overshoot value. This formula coming from this terms. Okay? But we divide X max is putting into this one, X SS also given to the what? The 1K. Right? It's coming from the equation, right? Because we have the one value in here, this going to the what? The infinity. And so xt transient, which is given in here, and it's equals to the what? It's 0. And so we, at the end of this times, xss must be equals to what? 1 divided by k, right? So this is the maximum overshoot formula. Maximum overshoot formula, MOF. And so, what about this one? We have another parameters in here, rise time. For the unit step, XSS is equals to what? 1 divided by K, right? It's coming from the what? The formula. So, E minus zeta WNT times sinus WN 1 minus zeta square times T plus phi must be equals to the 0 at the rise time, right? Because in the rise time, see that T rise is equals to what? 0.1 XSS, 0.9 XSS, and so 0.8 times XSS must be utilized in here. But we have this solution in here at the XSS, and so this must be also equals to what? M times pi. Okay? And so the TR must always be bigger than 0, and N must be equals to the 2 at this case. Okay? So, what's the values of the TR? TR, just like the previous formulation, 2 pi minus phi divided by Wn minus zeta square. Okay? This is not identical analytical solution, but it's closing or approaching to these values. Okay? So, what about the setting? Just remember that the tau is equals to the what? Zeta times Wn, and so setting time is equals to what? The 2% error at steady state. Which means that this means 4 times tau is equal to the what? Ts. Okay? Because we know that if we multiply the tau with the 4, and so steady state error goes to the what? 2% value. Okay? So, if this is the case, the Ts 4 divided by zeta times Wn price. Okay? These parameters are critical. And if we know how we can utilize these values, and so we can identify or model the R system based on what? The zeta times Wn. This is called system identification. What's your name? Yaran. What's your name? Yes. Sarah. Sarah. I'm sorry. Sarah, do you get it? Okay. You?
Why do we need
I'm showing with an example. 4.8.4 parameter estimation. In time domain. So suppose that we have this kind of measurement coming from any device, okay? That's the T, that's the XT. You push or apply to 1 Newton to the any mass, okay? And so this mass is going to do what? Some position and stop, just like this one, okay? In this one. These are the output, okay? And so if you analyze this value, this is equals to the 9, okay? 9 meter. And so this is also 12 meter, okay? This point, 12. And also this is the 9, and then what is the 0.9 times x assessing here? 9 times 0.9, which is equals to 81. What is the value of the 10% of this value? 0.1 XSS. No, 0.9. You see this graph in here. No, this is the 0.9 XSS. Okay, and so 0.9 times 9, it's equal to 0.81. But 0.1 XSS, 0.1 times 9. Yes, 0.81. No, I'm sorry. Get it right. 1, and this is 0.5. Okay, thank you. So we have also a time values in here because this is a graph, and so we can measure it. Okay, this is 1, and this is 2, and this is 3, and 4, and blah blah blah, and after all, at the 2% steady state error we have the 7. Okay, for this graph F is applied to 10 Newton, not the 1. Okay, and so we need to find out the mx dot plus c, x dot plus k, x is equals to what? The ft. We want to derive the m, c, k value from this graph. How we can do that? First of all, if we have the steady state value, SS value, what's the SS value? XSS is equals to what? 1 divided by k, right? From the previous formula, right? But in this case, we apply the 10 Newton. And so this is FSS. 10 Newton should be given here. And so 10 divided by k must be equal to the what? To the 9. And so what is the value of the k? 9 Newton meter. Right? This is the k value. This is spring factor of this system. And so, what is the overshoot value? The maximum overshoot, MP, which is equals to what? X max minus XSS divided by XSS. What's the X max? Huh? Yeah. XSS? Yeah. And so, yes, times 100. And so, which means that we have 30%, 33% overshoot in here. Okay? So, if this is the case, if we put this formula just like this one, and so can give another formula in here. R is equal to what? ln 100 MP which is equals to 10986, and so the zeta value is also equals to what? The r pi square plus r square, which is equals to the what? 0.33. Okay, the zeta can be found by using this term. In this case, we have this formula, and so we pull the zeta value from this one. Okay, we reorganize the equation in order to represent the zeta formulations in here based on this one, the r ln 100% mp, and so this r is used to what? To estimate the zeta. That's it. That's it. So what about the Wm value? The t setting time is equals to the what? Setting time? No. What's the value of the setting time? No, 7. It's coming from the graph. And so zeta times Wn 4 times Ts. And so this is equals to what? 5740. And so if this is the case, Wn is equals to the what? In here, divided by zeta, and which is equals to what? The 1.7311, right? This is the Wn. And so if we have Wn and zeta, we can try to the what? Our MCK system, right? And so in order to do that, m dot x dot plus, or in other terms, in the s domains, just like this one, s square plus c s plus k is equals to the 0. And also we have s square plus 2 zeta omega n s plus omega n square. Okay, we have these two formulations, and so we can collect this form s square c divided by m s plus km is equal to the 0, s square plus 2 zeta wn s plus wn square is equal to the 0. And so this c divided by m should be equal to the what? 2 times zeta wn. This km must be equal to what? The wn square, right? Sarah? Right? Right? Okay. And so the k is equals to the what? 10 divided by 9. Okay? We have found it. But so, what is the values of the m? K divided by m equals to the wn square, right? And so k divided by wn square is equals to the what? 0 kilogram is the Newton meter, right? Kilogram. Just putting every equation into this one. And so what is the values of the c in here? M times 2 times zeta times wn, right? Which is equals to 4288. Okay? Newton second meter. And so what is the R model? R model is equals to the what? The model is, this is the n x dot dot plus 0.4288 x dot plus 1.11 x, which is equal to what? 10 Newton. Okay? Or F. See? This is so simple. Just like this one. And so if we have the information about the Wn and zeta, we can derive and we can calculate the proposed M, C, K value from a given graph. Okay? Okay? Ready? Detaylı? Okay.